Hey everybody, today we are going to discuss basics of vectors and vector notation. Remember, a vector is anything that has both magnitude and direction. So one of the ways that you are probably most familiar with expressing vectors as is in Cartesian coordinates, so the XY system. So you might have a point like this down here, 3, 4, or -5, -2. The X is the first value given and the Y is the second value. In physics, because physicists like to just be different, we have our own system that's called vector notation. Sometimes it's referred to as rectangular coordinates. And so the standard notation for that is r sub x I hat plus r sub y j hat. It looks scary, but it actually isn't that bad. So let's do a sample problem. If I give you these two sample Cartesian coordinates, how would you write them in vector notation? So if I had the coordinates 3, 4, I would put 3 I hat, because 3 is my x value. The I hat just tells you that that's the x value, plus 4 j hat, and they're hats instead of dots. I'm not sure why, but that's just how it goes. All right, so what about if you had the Cartesian coordinates -5, -2? You would have -5 I hat minus 2 j hat. Likewise, what about if I gave you Cartesian rectangular coordinates such as 6 I hat minus 4 j hat, and I want you to turn that into xy coordinates? Well, you've got a positive 6 in front of the I hat, so that means an x value of 6, and a -4 in front of the j hat, so it would be 6, -4. All right, another type of vector expression, which you should have seen because you have taken trigonometry, is polar coordinates. And in polar coordinates, you have a magnitude or a resultant, comma, a theta, which is an angle. All right, this is one that students typically come to me and they don't really understand them, or they don't think they understand them. They're really not that tricky, so let's discuss. All right, so in the Cartesian coordinate, you have the x and the y axis. And so this quadrant is referred to as the first quadrant, second quadrant, third quadrant, and fourth quadrant. Okay, so right here you have 0 degrees. If you go up to the y-axis, that is a 90-degree value. Over here on the negative x-axis is 80 degrees, then 270 degrees, and if you come full circle, you have traversed a complete 360 degrees. All right, so today in class we talked about the significance of those coordinates. So if you are in the first quadrant, you would have positive x values and positive y values. If you're in the second quadrant, you have negative x values but positive y values. If you're in the third quadrant, you should have a negative x and a negative y value. And if you're in the fourth quadrant, you would have positive x values but negative y values. So these signs from Cartesian coordinates can actually be really helpful. If you go back, for example, to the point +3, +4, that would mean you go over 3 spots on the positive x-axis, 1, 2, 3, 4 spots on the y. Let me change my color. And that vector would look like this. If you were at -5, -2, we'd have to go -5 spots over on the x and down 2 on the y, and that vector would look like that. So the positive and negative signs actually can help you to understand where you are in the Cartesian coordinate system. Likewise, if you had a vector that was said to be like 5 newtons of force at 45 degrees. Well, we know that 45 degrees is halfway between the x-axis and the y. So perhaps a 45-degree angle would be right here. So we could draw that vector and we would just say that the length of it is 5 newtons, and it's at an angle of 45 degrees. Now, if we were down here at this other vector, we would need to have an angle because we're measuring from the 0. We know since we're in the third quadrant, it's got to be an angle somewhere between 180 and 270 degrees. So maybe this theta is like, I don't know, 200 degrees. Because when we have an angle of 200 degrees, we know that we're down here in the third quadrant. So sometimes in regular language, we might take that same vector. Sorry, my drawing's getting a little messy. Let's look at that same vector. And you might say that that angle right there is like 30 degrees southwest. Which, okay, I get it. That is the direction southwest, but that gets a little confusing because what does that mean? Well, if we would express this with respect to the unit circle and instead say that we are 30 degrees beyond 180, so 30 plus 180, that is actually at an angle of 210 degrees. So saying that this vector is at an angle of 210 eliminates a lot of the confusion because you know exactly where that is. There's only one point that is 210 degrees from the 0 point. All right, so how do we convert back and forth? We had talked about up here how to convert back and forth between Cartesian and rectangular. But what about if we need to convert between Cartesian and polar? So if you are given a set of polar coordinates like r, theta, and you are supposed to turn them into an x and y component, the x value is going to be equal to r cosine theta, and the y value is going to be equal to r sine theta. Now my tip for you is to make sure that you are in degrees, not in radians. All right, what about on the other hand, if you're given Cartesian, so you've got an x and a y value, and you need polar? Well, in that case, the r, or the resultant, is going to be equal to the square root of rx squared plus ry squared, and the theta is going to be equal to the inverse tangent of ry over rx. All right, so let's do a sample problem. So the homework assignment associated with this lecture is worksheet 3.1. And if you are to look at problem 1C, it gives you a vector that is drawn something like this. And it says the magnitude of that vector is 25 newtons, and this angle is 30 degrees. My drawing's not exactly accurate, but you can get the idea. All right, and we are supposed to come up with the x and y values of this. All right, so let's go back to our equations. If we have the polar coordinates and we need x and y, this is what we are supposed to use. So the x component is going to be equal to 25 newtons. But I guess I should go back here because remember how we said we shouldn't express our angles like this? We want to know what that angle is with respect to the unit circle. So we know that we're 30 degrees beyond the 270 degree mark. So my theta here is 30 degrees plus 270, which gives me a theta of 300 degrees. So Rx is equal to R cosine theta. So I want to take 25 newtons times the cosine of 300 degrees. All right, when I plug that in to my calculator, I get 25 cosine 300. I get a value of 12.5, and I'm going to write an in there because my unit label is newtons. We haven't gotten there yet, but that's the unit of force. All right, our y then can be found by taking 25 newtons times the sine of 300 degrees. So 25 times sine of 300 gives me a value of negative 21.7 newtons. Now, if we think about it, that means that my xy coordinates are positive 12.5 with a negative 21.7. Does that make sense with my graph here? Well, yes, it does, because I would have a positive x value and a negative y value in order to achieve this resultant vector. All right, likewise, let's move down to the next portion. In the next portion, let's take a look at problem number 9. So in problem 9, they give you a vector that is 20 newtons to the left, and then another vector that is 35 newtons to the downward direction. We are supposed to find the resultant. Well, the resultant is like adding those two together. And you may have learned in math class that adding two vectors, you start at the tail of the first vector and then you point it towards the head of the last vector. So this is our resultant. Well, this looks an awful lot like a right triangle, and R is actually the hypotenuse. So that's where the Pythagorean theorem comes into play. So R is going to be equal to the square root. Now, we should actually think about this for a minute, because this 20 degrees is pointed in the negative direction. So actually, I should call that negative 20 for the x coordinate. And since the 35 is pointed downwards, it should also be a negative value. Now that's not going to mean too much right now because we're squaring these. So you've got the square root of negative 20 squared plus negative 35 squared. All right. So give me a minute while I figure that out. All right, so I have a resultant value of approximately 40 newtons. Now for theta, my theta should be equal to the inverse tangent of the y value, which is negative 35, over the x value, which is negative 20. So inverse tangent of 35 divided by 20 gives me an angle of 60 degrees. But we have to think about it. 60 degrees would be up here in the first quadrant, and our vector's down here in the third. So that 60 degrees is this angle right here. And if we are supposed to follow our guidelines from up here to always think and express theta with respect to the unit circle, then we shouldn't call that 60 degrees. We should call that 60 degrees beyond 180, which gives me 240 degrees. So the best answer for resolving this into polar coordinates would be a vector of magnitude 40 newtons as the resultant and an angle of 240 degrees. I hope this helps clarify different ways to express vectors and how to convert from one notation to another. The main takeaways here are to always draw a picture so that you know what coordinate you or what quadrant you are in, and then express your angle with respect to the unit